Okay, welcome again. Now, optical network elements. What are the equipment? What are the elements which we are using in DWDM system? The optical equipment or elements which we are using in DWDM systems are transponder, and it consists of multiplexer, demultiplexer, then optical amplifier, OADM, and ROADM. DWDM technology is cost effective, flexible for upgradation of channel capacity, adds of channels, rerouting, and traffic distribution. It supports all type of network topology, protection systems, and synchronization. Any type of topology, any type, whatever you want can be transmitted on the DWDM system. Main network elements: transponder, multiplexer, demultiplexer, optical amplifier, OADM, optical add-drop multiplexer, and ROADM, reconfigurable optical add-drop multiplexer, OFC, optical cross channel. Now, one by one, transponder. Transponder is the interface between STM system. STM is written. STM means STM 1, 4, 16, 64, whatever you are using, or combination of this one. Wide bus shortcut signal and must equipment. This shortcut signal may be co-located or coming from different physical mediums. These systems, STMs, may be at the same station, or these systems from some other different station. It converts the wide pulse optical signal into a narrow wavelength of the order of nanometer with spacing of 1.6 nanometer sending to multiplexer. And this multiplex signal, when received from other end, it comes to the DMUX. In the reverse direction, colored output from the DMUX is converted into wide pulse optical signal. Output power level +1 to -3 dBm in both directions. This is the block diagram. Conversion, here you see this conversion is A to E, optical to electrical in trans side, and in receive side it is E to O. 2R method or 3R method. In 2R, you know regeneration and reshaping are done, and in 3R, regeneration, reshaping, and retiming are performed. It is shown in this diagram. Again, same thing. This is from optical OLT, different OLTs. These OLTs may be at the same station. This 1, 2, 3 may be at the same, or this one may be from other station. This two from some other, this two from some other. And these optical, this system works on the principle of OEO, optical to electrical, and again electrical to optical. Multiplex and demultiplex takes optical wavelength from multiplex multi-fibers and convert into beam and send to the single fiber, and this signal received at the distant end, where the multiplexer performs this function by separating the received beam into the wavelength components and coupling them into individual fibers. Multiplexer and demultiplexers can be either passive or active in design. These multiplexer, demultiplexer may be passive, may be active. Here, in this case, this is multiplexer, different wavelengths, and after multiplex, these wavelengths are transmitted in a single fiber. And to see that these wavelengths received in single fiber and demultiplex to different wavelengths. Multiplexing of four wavelengths. This diagram shows how the four wavelengths are multiplexed. It is very clear. If you just see here, one wavelength say lambda 2. This is converter multiplex here lambda 1 and lambda 2. This one from lambda 1, this is lambda 2. These two are multiplied in the circulator pole, lambda 1, lambda 2. Then again FBG, here we get lambda 3. Then lambda 1, lambda 2, lambda 3 are multiplied. Here we have lambda 4. Then lambda 1, lambda 2, lambda 3, lambda 4 are multiplied. So this is the procedure of four wavelength multiplex. And for this multiplexing, we use diffraction grading like this. This diffraction and grading you have studied in physics in your old classes. So for this multiplexing, you should remember what we are using. We are using diffraction grading. Optical amplifiers, different type of optical amplifiers are there to amplify these optical signals. These are written here. Semiconductor laser amplifier, SLA, fabric parrot amplifier, FPSLA, which you have studied in your GK classes. Traveling wave amplifier, TWSLA. Then rare earth doped fiber amplifier, PDFA, EDFA, volume doped fiber amplifier, and most commonly or most important which we are using in DWDM is EDFA, erbium doped fiber amplifier. So you should remember what type of fiber we are using in the DWDM system, that is EDFA, erbium doped fiber amplifier. Now these optical fiber amplifiers, are using fiber nonlinearity, Raman amplifier, William amplifier, and channel basis, single channel and multi-channel channel, and further classified in case of pumping, co-directional pumping, counter-directional pumping, and dual pumping. So these are the different types of optical amplifiers which are described on the basis of nonlinearity, on channel basis, on pumping basis. Types of amplifiers which we are using in DW system, as I have explained earlier. Booster amplifier, which is used just after the multiplexer. Line amplifier, which are used at the point of repeater, ALA, optical line amplifier. Then pre-amplifier, just used before the demultiplexer. So three types of optical amplifiers: booster amplifier BA, line amplifier LA, and PA pre-amplifier. Requirements for these optical amplifiers in DWDM systems are high gain should be high, low noise, and flat amplification profile. Here, the diagram shows different type of optical amplifiers and where these amplifiers are being used. Booster amplifiers used just after the transmitter, that is after multiplexing. Pre-amplifiers just before the receive, and inline amplifier, line amplifier LA, OLA, in between station, terminal stations, that is at the location of repeater. Here, erbium doped amplifier is explained. This amplifier depends on material gain defined by the erbium doping of a relatively short section of silica fiber from with optical rather than in electrical energy. There is optical pumping used in EDFA. An erbium doped fiber amplifier can amplify a weak light signal if pumped with a laser. If input light of 1.55 nanometer, that is 1550 nanometer wavelength, passes through the erbium doped fiber, then the excited electron transfer energy to the input light, thus amplifying the input light. This is the procedure how the EDFA working. EDFA allows information to be transmitted over longer distances without the need for conventional repeater. This device, EDFA, uses 980 nanometer or 1480 nanometer pumping laser. You should remember here, EDFA uses 980 nanometer or 1480 nanometer. Each signal 1310 or 1550 nanometer, whatever the signal is there, their stored energy as additional 1000 nanometer or 1310 nanometer line. The process continues as the signal passes down the fiber growing repeater. So this is the block diagram. Here, this is the wavelength selective coupler. This is your LBM growth 5-square amplifier. This is isolator, and this is pumping light source. And it uses wavelength 980 or 1460 nanometer. This you should remember. This is again same thing, summarized. This is pumping laser, this is our oscillator, and here is the supply. And this is known as EDFA LBM growth fiber. Same thing. Now, what are the advantages of EDFA? Simultaneous application of the whole 15350 nanometer area which are being used in DWDM system. Total output power of this EDFA possibly is 1 to 1000 microwatts. Large dynamic ranges suitable for long haul applications. Therefore, at the moment of EDFAs are the commonly used amplifier type. This is I again and again telling you, EDFA is the amplifier which are used in DWDM system. It may be DA, maybe LA, or maybe PA. Common amplifiers, we may use it. Then what is OADM and ROADM? In SPS systems, we were using ADM, air drop multiplexer, where different frequencies can be added or dropped either on electrical level or on optical level. In the same way, in DWDM system, different frequencies can be added or dropped as OADM, but this adding or dropping will be on optical level. So there are two types of OADM. One is OADM and second one is ROADM. ROADM means reconfigurable optical air drop multiplexer. Some OADMs are designed for a fixed wavelength. Suppose OADM is designed for wavelength say lambda 1 or lambda 2. So we can add or drop only that wavelength for which that OADM is designed. But in ROADM we can reconfigure or we may add or drop any wavelength as per our requirement. So this is ROADM. Like this. This is OADM. Suppose different wavelengths, there are suppose 4 wavelengths, lambda 1 to lambda 4. These are transmitted through this OADM. As per our requirement, we may add or drop any wavelength, lambda 1, lambda 2, lambda 3, lambda 4. For whatever wavelength our this OADM is designed. Here it is again described ROADM allows any wavelength to be dropped and added without impacting other wavelengths, provided power balancing and monitoring and come with good planning tools. Now DXP, what is DXP? Digital cross connect. In digital cross connect, suppose if any link, any arm is failed, then frequency can be transmitted to some other line. So there is a requirement, there is some configuration of digital cross connect. So there is a cross connection designed in this DXP. Suppose any frequency is working through this arm. Suppose if this arm is failed due to any reason, then this frequency can be switched to this second line. So this is the use of DXP. So this is another equipment of the DWDM system, which is known as DXP, digital cross connect. This digital cross connect which we are using as a system. But here in DWDM, this is known as OXC, Optical Cross Connect. This is the diagram of OXC. And in this way, this is the complete block diagram of network elements of DWDM. Here, this is PC, transponder, or you may say OTM, channel multiplexer, transponder, whatever you say. Different wavelengths, different systems, which are multiplexed here. This is optical multiplexing. After multiplexing, if we are amplifying the signal with EDFA amplifier, then this amplifier is booster amplifier. Then in line, that is at the place of repeater, if we are using this amplifier, then this is line amplifier. Here, in between links, we may have OADM, optical add-drop multiplexer, where we can add or drop different wavelengths or wavelengths as per our requirement. And there may be OSC also, optical cross connect. Then these signals come to the last terminal, which is where the multiplexing. And if we are using any amplifier here, that amplifier, again same amplifier, but here it is known as pre-amplifier. So this transponder, same slide is repeated. So in this way, this is all about just you should see this. There is OSC also used, optical supervisory channel. This DWDM systems can be supervised at the same station, same point. So some requirement, there is some requirement of some wavelength is designated for this optical supervisory system. That is used know this as NMS, Network Management System. Here standard IP bit, which I will explain, center frequency 193.1 terahertz. You should remember this. And corresponding wavelength is 1553.52 nanometer, which is nearly 1.1550 nanometer. The standard spacing may be 0.2 terahertz, 0.1 terahertz, or 0.05 terahertz, that is 200, 150 gigahertz. So in this way, DWDM systems can be described in different type of there. If you use DWDM system, there will be some classification on the basis of haul, long haul system, very long haul, ultra long haul, on the basis of spacing, 200 gigahertz spacing system, 100 gigahertz spacing system, or whatever it is. And third one is band. The system is designed for L band or C band, long band or conventional band. So this is the IPG690 frequency grid. Here, this is the 193.1 terahertz of center frequency, and if spacing is 100 gigahertz, that is 0.1 terahertz. Different type of wavelengths and different wavelengths which can be calculated with help of equal to lambda. These are the different frequencies and wavelengths which are being used in the DWDM system. Thank you. So in this way, this is all about introduction of DWDM system. If you have any query, any question, you may ask. And if there is no question, you may go through these. If any problem, you may directly ask to me or come to my office. Okay?
Okay, sir.
Thank you. Thank you very much.
Thank you, sir. Thank you.
Thank you, sir.